Tonight, we are going to stare across the gulf to our nearest stellar neighbor. The closest star to our Sun, other than the Sun itself, sits at a distance of 4.24 light-years. That number sounds almost reasonable. It rolls off the tongue. It seems like a destination. But here is what those 4 words actually mean. 25 trillion miles, 40 trillion kilometers. A gulf so vast that the fastest object humanity has ever built, a probe screaming through space at 430,000 mph, would still need over 600 years to cover it. Longer than recorded human history. Longer than the existence of every civilization that has ever risen and fallen on Earth. And here is what almost nobody tells you. That is the optimistic scenario. The reality, when you actually examine the physics, the engineering, the energy requirements, and the biological constraints, is that reaching the nearest star may not just be difficult. It may be physically impossible. Not impossible in the sense of being far away. Impossible in the sense that the universe itself appears to have written rules specifically designed to keep us trapped here, in the warm, narrow band around a single ordinary star, on a single fragile planet with no way out. Before we go any further, if you find this kind of deep cosmic exploration as fascinating and unsettling as I do, please take a moment to like this video and subscribe to the channel. Deep Space Signals exists because of viewers like you who want to confront the universe honestly. It helps more than you know. Now, settle in, get comfortable, and let's begin. The nearest star is not a single star. That is the first thing to understand. When we say nearest, we are usually talking about the Alpha Centauri system, a triple star arrangement that lies in the southern sky, invisible to most of the northern hemisphere. 2 of those stars, Alpha Centauri A and Alpha Centauri B, are Sun-like. They orbit each other in a relatively close binary dance, separated by distances that vary between 11 and 36 astronomical units across their 80-year orbital period. The third member, Proxima Centauri, is a small red dwarf that drifts at the outer edge of the system, roughly 13,000 astronomical units from the central pair. Proxima is the closest individual star to us at 4.24 light-years. The Alpha Centauri AB pair sits at 4.37 light-years. For most discussions of interstellar travel, these distances are essentially identical. They both represent the closest stellar destination we could possibly aim for. Anything beyond Alpha Centauri is even farther. Barnard's star at 5.96 light-years. Wolf 359 at 7.86 light-years. Sirius, the brightest star in our sky, at 8.6 light-years. The list extends outward into distances that make Proxima look practically next door. But Proxima is not next door. Let me give you a way to feel this. The Earth orbits the Sun at an average distance of about 93 million miles. Light from the Sun takes roughly 8 minutes and 20 seconds to reach you. That is 1 astronomical unit, our basic ruler for measuring distances within the solar system. Neptune, the outermost major planet, sits at about 30 astronomical units from the Sun. A signal sent from Earth to Neptune takes about 4 hours each way. Voyager 1, the farthest human-made object from Earth, has been traveling outward for nearly half a century and has reached approximately 159 astronomical units. The distance to Proxima Centauri is 268,000 astronomical units. That is 685 times farther than Voyager 1 has traveled in 49 years. To reach Proxima at Voyager's current speed, you would need to keep traveling, without slowing down, without stopping, without any maintenance, without any propulsion system failures, for approximately 73,000 years. The pyramids of Egypt have stood for about 500 years. The first agricultural settlements appeared roughly 12,000 years ago. The oldest cave paintings we have discovered are dated to around 45,000 years ago. The journey to Proxima at Voyager speed would last longer than every span of time you can intuitively grasp combined. And Voyager is not even pointed at Proxima. It is heading in a different direction entirely. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of an obscure red dwarf called Gliese 445. That is closest approach. Not arrival. Not entry into another star system. Just a long-distance flyby of a star that is not even particularly close. And Voyager will not have enough power to send back a single bit of data when that moment arrives. The spacecraft will be cold and silent, drifting through emptiness, an artifact of a civilization that may no longer exist by the time it reaches its closest point to that distant star. This is the scale we are talking about. And before you say, well, surely we can build something faster, surely we can develop better propulsion, surely with enough engineering we can solve this, you need to understand exactly what physics demands of any spacecraft trying to cross interstellar distances within human timeframes. Because the universe is not just indifferent to our efforts, it is actively hostile to them in ways that most people have never contemplated. Let me start with the simplest barrier, the rocket equation. Konstantin Tsiolkovsky, a Russian scientist working in obscurity at the turn of the 20th century, derived a mathematical relationship that governs every rocket humanity has ever built or could ever build, using the principle of expelling mass to generate thrust. The equation looks innocent enough. It relates a rocket's maximum velocity to two quantities: the exhaust velocity of its propellant, which is essentially how fast the rocket can throw material out its back end, and the ratio between the rocket's initial mass with all its fuel loaded and its final mass after burning that fuel. The equation contains an exponential function, and that exponential function is where the trap lies. As you push for higher and higher velocities, the amount of fuel required does not increase linearly, it increases exponentially. Each additional kilometer per second of velocity demands not just more fuel, but exponentially more fuel. For chemical rockets, the kind we use today to launch satellites and visit Mars, exhaust velocities max out around 4.5 kilometers per second. This is not an engineering limit waiting for a clever solution. It is a fundamental ceiling imposed by chemistry itself. When you burn hydrogen and oxygen, the most energetic chemical reaction we can practically harness for propulsion, the resulting steam molecules can only move so fast. The energy released by breaking and forming chemical bonds has an absolute upper limit. No amount of nozzle design, no breakthrough in combustion chamber materials, no clever fuel mixture can push water molecules out of a rocket faster than chemistry permits. Now apply the rocket equation to the problem of reaching Proxima Centauri within a human lifetime. If you want to arrive in 50 years using chemical propulsion, you would need the spacecraft to travel at roughly 26,000 kilometers per second on average. That is about 8.7% of the speed of light. Plug those numbers into the Tsiolkovsky equation with chemical rockets, and the required fuel mass becomes mathematically larger than the mass of the entire observable universe. Not the mass of Earth, not the mass of the Sun, not the mass of all the stars in our galaxy combined. The mass of every atom in every galaxy that could ever conceivably be detected by any telescope. Even that is not enough fuel to push a small spacecraft to Proxima within a single human lifetime using chemical combustion. This is what physics actually requires. It is not a difficulty to be overcome through better engineering. It is a wall that chemistry itself has built around us, and chemistry is not negotiable. So chemical rockets are out, not just slow, but fundamentally incapable. This is sometimes called the tyranny of the rocket equation, and the phrase is not hyperbole. The exponential function is genuinely tyrannical. It does not care about your funding levels, your engineering ingenuity, or your political will. It simply demands more fuel, exponentially more, until the demand exceeds the matter available in the universe itself. To escape this tyranny, you need to fundamentally change something about the propulsion system. Either dramatically increase the exhaust velocity, or find a way to leave the energy source at home rather than carrying it with you. Both approaches have been studied for decades, and both run into walls that may be just as impassable as the chemical limit. Consider nuclear thermal propulsion. NASA tested these engines extensively in the 1960s under the NERVA program, conducting dozens of successful reactor firings in the Nevada desert. The technology works. You pass hydrogen propellant through a hot nuclear reactor, heating it to extreme temperatures, then expel it through a nozzle. The nuclear heat source allows the hydrogen to reach roughly twice the exhaust velocity of chemical combustion. That is a meaningful improvement. It would dramatically expand what we can do within the solar system, cutting trip times to Mars roughly in half, opening the outer planets to crewed exploration. But for interstellar travel, doubling the exhaust velocity is laughably insufficient. The rocket equation still demands fuel masses that scale exponentially with desired velocity, and even with nuclear thermal exhaust speeds, reaching Proxima within a human lifetime would still require fuel quantities that no spacecraft could ever carry. So we move further up the propulsion ladder. Nuclear pulse propulsion, Project Orion. The audacious 1950s and 1960s effort by some of the finest physicists of the era to harness nuclear explosions for spacecraft thrust. Freeman Dyson, Theodore Taylor, and dozens of others worked on this concept seriously. The idea sounds insane on its surface. You build a massive spacecraft with a thick pusher plate at its rear. You eject nuclear bombs out the back and detonate them at a calculated distance. The expanding plasma fireball strikes the pusher plate, transferring momentum to the spacecraft. Shock absorbers smooth out the violent impulses into tolerable acceleration. You ride a series of nuclear explosions to the stars. Calculations showed that Orion could potentially achieve velocities of 3 to 10% of light speed, depending on the design and whether you used fission bombs or hydrogen fusion devices. At 10% of light speed, the journey to Proxima Centauri would take approximately 43 years one way. A human could potentially survive such a trip, leaving Earth at age 25 and arriving at age 68. Not a comfortable old age to begin exploring an alien stellar system, but conceivable. Project Orion was killed by the 1963 Partial Nuclear Test Ban Treaty before any nuclear detonations could be tested. The political impossibility of launching a spacecraft requiring thousands of nuclear weapons through Earth's atmosphere, scattering radioactive fallout in its wake, ended the program. But the physics remained sound. The engineering, while extraordinarily challenging, was not fundamentally impossible. We have known for over half a century that humanity could in principle build a vehicle capable of crossing interstellar distances. We have simply chosen, repeatedly, deliberately, never to do so. And there are good reasons beyond nuclear politics. Even an Orion-class vessel reaching 10% of light speed faces problems that have nothing to do with propulsion at all. This is where the second wall begins to appear. The interstellar medium. Space between the stars is not empty. It contains gas, dust, charged particles, and occasional larger objects, distributed at extraordinarily low densities but spread across distances so vast that even tiny encounters add up to enormous consequences. In our local region of the Milky Way, the average density of the interstellar medium is roughly 1 hydrogen atom per cc. That sounds like nothing. It is nothing by the standards of any vacuum chamber humans can build in a laboratory, but at relativistic velocities that almost nothing transforms into a deadly storm. Kinetic energy scales with the square of velocity. Double the speed of an object and its kinetic energy quadruples. Multiply the speed by 10 and the kinetic energy multiplies by 100. At 10% of light speed, every hydrogen atom your spacecraft encounters carries kinetic energy comparable to that of a high-energy cosmic ray particle. Each individual impact delivers enough energy to damage materials at the atomic level, knocking atoms out of crystal lattices, breaking molecular bonds, ionizing biological tissue. The number of these impacts is enormous. A spacecraft with a 1 square meter cross-section traveling at 10% of light speed would collide with approximately 100 trillion hydrogen atoms every second. A continuous, relentless, microscopic bombardment of the leading surfaces of the vessel. The cumulative effect over a 43-year journey would be devastating. Materials would erode. Electronics would degrade. Crew members would receive radiation doses that current medicine has no way to mitigate. And hydrogen atoms are not the only hazards. The interstellar medium contains dust grains. Most of them are tiny, perhaps a micrometer or less in diameter. At Voyager speed, hitting a micrometer-sized dust grain is essentially harmless. At 10% of light speed, the same grain delivers kinetic energy equivalent to a small explosion. Larger grains, even those a millimeter across, would hit with the energy of a substantial bomb. And we cannot see most of these grains. We cannot map them in advance. Our knowledge of the local interstellar medium comes largely from the Voyager probes, which have given us point measurements at 2 locations along 2 trajectories, billions of miles apart. plus astronomical observations that integrate light over enormous distances and cannot resolve individual obstacles. A spacecraft traveling at relativistic velocity to Proxima Centauri would be flying blind through a minefield, where the mines are too small to detect, and the cumulative impact of even non-mine-sized particles could destroy the vehicle. Shielding is possible. You can put a thick layer of material at the front of the spacecraft to absorb impacts. The mass-energy considerations get ugly fast, because that shielding has to be accelerated to relativistic velocities along with the rest of the vessel, and the rocket equation does not stop punishing you just because you have moved past chemical fuel. Every additional kilogram of shield is another kilogram, demanding exponentially more energy to push to your target velocity. You could potentially use a magnetic deflection system to sweep charged particles aside, but neutral hydrogen atoms and dust grains are immune to magnetic deflection. They need physical barriers, and the physics of relativistic velocity impacts is so violent that even the best refractory materials we know how to manufacture would erode steadily under the bombardment. The ship would arrive at its destination as a smaller, thinner, more battered version of itself, assuming it arrived at all. This problem alone might not be insurmountable for a robotic probe willing to accept significant attrition. For a human crew, it transforms a difficult journey into a potentially fatal one. The radiation environment inside a relativistically traveling spacecraft would exceed everything we have ever measured in our solar system. Cosmic rays, already a threat to astronauts on the International Space Station and a far greater threat to anyone outside Earth's protective magnetic field, would be supplemented by the secondary radiation produced when relativistic hydrogen impacts the hull. Cancer rates would skyrocket. Acute radiation sickness would become a constant medical challenge. The crew would essentially be slow cooking in a continuous bath of energetic particles for the entire duration of the trip. So perhaps we abandon the idea of carrying our energy source. Perhaps we try beamed energy propulsion, where the power stays on Earth and pushes the spacecraft from a distance using lasers. This is the central concept behind Breakthrough Starshot, a project announced in 2016 with significant initial funding and the endorsement of the late Stephen Hawking. The proposal calls for a massive ground-based laser array, drawing power on the order of 100 gigawatts, focused on a tiny spacecraft equipped with a lightweight reflective sail. The laser would push the sail for a few minutes, accelerating the gram-scale vessel to roughly 20% of light speed. At that velocity, the journey to Alpha Centauri would take about 20 years. Add 4 years for the return signal, and we could conceivably receive data from the nearest star system within a single human career. The engineering challenges are staggering, but at least they are theoretically tractable. The laser array itself would require power output equivalent to 100 large nuclear power plants, all focused with extraordinary precision on a target receding at thousands of kilometers per second. The sail must be incredibly thin, just a few grams per square meter, while remaining strong enough to survive radiation pressures that would vaporize conventional materials. The reflective coating must be so close to perfect that even minor absorption would heat the sail to destruction. The pointing accuracy required is similar to hitting a coin from thousands of miles away while the coin is moving. None of these problems are obviously impossible, but they are problems at the absolute frontier of what is physically achievable, and they are only the beginning. Because here is the fatal flaw of beamed energy propulsion for human travel. A laser-pushed sail accelerates by reflecting light from behind. It cannot use the same mechanism to slow down, because there is no laser at the destination pushing back against it. A Breakthrough Starshot probe would flash through the Alpha Centauri system at 20% of light speed, having mere hours to take photographs and transmit data before departing into interstellar space, never to be seen again. The spacecraft would not stop. It cannot stop. The system has no deceleration mechanism and no way to add one without fundamentally changing the entire propulsion approach. For a robotic probe gathering brief observations, this might be acceptable. For human travelers hoping to actually arrive somewhere, to walk on a planet, to explore a new stellar system, beamed energy in its current conception fails completely. You would arrive at your destination at relativistic speed, take a few thousand pictures during your brief fly-through, and then continue forever into the void on the far side of the system. There are proposed solutions. Magnetic sails that interact with the destination star's stellar wind to gradually decelerate. Onboard fusion drives that fire in the opposite direction during the second half of the journey. hybrid concepts combining laser acceleration with self-powered deceleration. Each adds enormous complexity. Each adds mass that the laser must accelerate in the first place. Each introduces new failure modes. And each remains theoretical, with no demonstrated technology that even approaches the requirements for a real interstellar mission. This is the pattern that emerges as you survey every proposed approach to reaching the nearest star. Chemical rockets are fundamentally inadequate, blocked by the exponential cliff in the rocket equation. Nuclear thermal propulsion helps but does not help nearly enough. Nuclear pulse propulsion could potentially work but faces engineering, political, and safety challenges that have prevented its development for over 60 years and may continue to prevent it indefinitely. Ion propulsion is too weak, building velocity over decades but never reaching the speeds that would matter for interstellar distances. Antimatter propulsion offers the highest theoretical performance of any known mechanism, but faces production and storage problems that may not be solvable in any time frame relevant to human civilization. Beamed energy can accelerate but cannot stop. Fusion drives, the most realistic medium-term hope, top out at velocities where the journey still consumes most of a human lifetime and time dilation provides only marginal relief. Every door opens onto another wall. This is not a coincidence. This is what the universe actually looks like when you examine it honestly. The same laws of physics that make stars possible, that allowed life to emerge on Earth, that make the cosmos a coherent place where things can exist and persist, also make interstellar travel staggeringly difficult. The speed of light is a hard ceiling. The rocket equation is an exponential trap. The interstellar medium is a deadly hazard at relativistic velocities. The energy requirements scale catastrophically with desired arrival times. None of these are engineering problems waiting for a clever solution. They are constraints written into the structure of physical reality, and the universe enforces them with mathematical indifference to our ambitions. Now, somebody listening to this is going to object, but what about Einstein? What about time dilation? What about relativity? Surely if we could approach the speed of light closely enough, the journey would compress dramatically for the travelers, even if it took years from Earth's perspective. And that objection is correct. Time dilation is real, measurable, and verified by precision experiments going back over half a century. At velocities approaching the speed of light, clocks aboard a fast-moving spacecraft genuinely run slower than clocks on Earth. The traveler's experience of the journey duration shrinks. At 99% of light speed, the gamma factor that governs time dilation reaches roughly 7. A 4.24-year journey at that speed, as measured on Earth, would feel like only about 7 months to the crew. At 99.9% of light speed, the gamma factor exceeds 22. The journey would compress to less than 3 months of subjective time. At 99.99% of light speed, the trip would feel like roughly 6 weeks. Push velocity arbitrarily close to light speed, and the subjective journey time drops towards 0. From the traveler's perspective, you could cross any cosmic distance in any amount of time you wanted, provided you could move fast enough. This is genuine. The mathematics is correct. The experimental verification is solid. Relativistic time dilation provides a real loophole that, in principle, allows human consciousness to traverse cosmic distances that light itself requires years or millennia to cross. The catch, and it is a brutal catch, is that approaching the speed of light costs energy, and the cost approaches infinity as you approach light speed. This is the other side of Einstein's equations, the side that traps you while pretending to liberate you. Mass and energy are equivalent. As an object accelerates, it gains kinetic energy. At low velocities, this energy increase follows familiar Newtonian patterns. Doubling your velocity quadruples your kinetic energy. The relationship is straightforward, manageable, predictable. But as velocity approaches a significant fraction of light speed, the energy required to accelerate further begins climbing far faster than Newton's equations predict. The object behaves as though it has more mass than it started with. This effect, sometimes called relativistic mass increase, grows more severe as velocity increases. At 50% of light speed, the effective mass has grown by about 15%. At 90%, it has more than doubled. At 99%, it has multiplied by roughly 7. At 99.9% by 22. The factor exceeds 200 at 99.999% of light speed and continues climbing without limit as velocity approaches the cosmic speed limit. Each additional increment of velocity demands not just more energy but exponentially more energy. To reach 90% of light speed with a small 1,000-kilogram probe requires kinetic energy on the order of 10 to the 19th joules. That equals the total energy output of the Sun for roughly 2 seconds, or the entire energy consumption of human civilization for approximately 1 million years, concentrated into accelerating a single small spacecraft. To reach 99% of light speed, the requirement multiplies by another factor of 7. To reach 99.9%, by another factor of 3. The energy demands quickly leave the realm of any conceivable engineering and enter the realm of cosmic absurdity. And this energy must come from somewhere. If the spacecraft carries its own fuel, the rocket equation rears up again with even more violent exponential demands, because now you are accelerating not just the payload, but enormous quantities of fuel, and the structures needed to hold and burn that fuel. If the energy comes from a beamed source on Earth, the power requirements push past anything our civilization has ever produced or could plausibly produce. The 100-gigawatt laser array proposed for Breakthrough Starshot is sufficient to push a few-gram probe to 20% of light speed. To push a crewed spacecraft, massing perhaps 100,000 kilograms, to 90% of light speed would require power outputs on the order of 100 trillion watts, roughly the entire current energy consumption of human civilization, focused continuously on a single spacecraft for the duration of its acceleration phase. And then you have to do it all over again to decelerate at the destination. Time dilation works. It is real. But the price the universe charges for accessing it is so steep that it remains a theoretical loophole rather than a practical pathway. The mathematics permits you to cross interstellar distances in subjective months. The physics demands that you pay for that access in energies that exceed anything our species has ever harnessed or could plausibly harness within any time frame relevant to current civilization. The door exists. The toll booth in front of it accepts only currency we do not possess and cannot manufacture. Consider antimatter more carefully, because it represents the absolute theoretical ceiling of energy-dense propulsion that operates within understood physics. When a particle of ordinary matter contacts its antimatter counterpart, both annihilate completely, converting 100% of their combined mass into pure energy. This is the most efficient energy release that current physics permits any process to achieve. Compare it to nuclear fission, which converts roughly 0.1% of mass into energy, or nuclear fusion, which manages around 0.7%. Antimatter annihilation is roughly 1,000 times more efficient than fission and roughly 140 times more efficient than fusion. A single gram of antimatter, allowed to annihilate with a gram of normal matter, releases approximately 180 trillion joules of energy. That equals the explosive yield of the Hiroshima atomic bomb, contained in a fragment of material small enough to balance on your fingertip. It represents the entire energy consumption of an average household for roughly 4 years, packed into a single instant of conversion. If antimatter could be produced in bulk and stored reliably, it would solve much of the energy problem for interstellar travel. A few thousand kilograms of antimatter, properly directed through a magnetic nozzle, could potentially accelerate a modest crewed spacecraft to 70 or 80% of light speed and decelerate it again at the destination. Time dilation at those velocities would compress the subjective journey to Proxima Centauri to perhaps 3 or 4 years. A mission crew could leave Earth, explore the Alpha Centauri system, and return having aged maybe a decade, while Earth aged perhaps 15 years. The math works beautifully. The physics is not in dispute. Antimatter behaves exactly as Einstein's equations predict, and we have made and studied antiparticles in laboratories for over a century. The problem is producing it. The problem is storing it. The problem is the gap between what is physically possible and what is engineering achievable. Antimatter does not exist naturally in significant quantities anywhere we can reach. The early universe was created with a tiny imbalance between matter and antimatter, and the antimatter component annihilated almost completely within the first second after the Big Bang, leaving the universe of ordinary matter that we inhabit today. To get antimatter for propulsion, we have to manufacture it, atom by atom, through high-energy collisions in particle accelerators. The total quantity of antimatter ever produced by all human civilization, across every laboratory and every accelerator ever built, totals less than 20 nanograms. That is 20 billionths of a gram. barely enough to sustain a small light bulb for a fraction of a second if it could be perfectly converted to electrical energy. To fuel a single interstellar mission, we would need to scale that production by a factor of perhaps 100 trillion. At current production rates, accumulating enough antimatter for a one-way trip to Proxima Centauri would require continuous production for billions of years. Longer than the universe has existed in its current form, the energy cost compounds the problem catastrophically. Producing antimatter through particle collisions is staggeringly inefficient. Roughly 10 billion times more energy goes into making the antimatter than the antimatter ultimately stores. Even setting aside the time required, the energy demand for manufacturing fuel for a single interstellar mission would exceed the total energy consumption of human civilization for thousands of years. We would need to redirect the entire industrial output of our species, every power plant, every refinery, every electrical generation source, into a single antimatter factory operating continuously for centuries, just to fuel one trip, and then we would need to do it again for the return journey, and again for any second mission. The energy economy of civilization itself becomes the limiting factor before any propulsion physics enters the picture. Storage adds yet another wall. Antimatter annihilates instantly upon contact with any normal matter, converting itself and its container into a fireball that releases energy proportional to its quantity. A kilogram of antimatter, accidentally touching ordinary matter, would produce an explosion equivalent to roughly 40 megatons of TNT, comparable to the largest nuclear weapons ever tested. The fuel must be suspended in a perfect vacuum using magnetic containment fields, never touching the walls of the storage vessel, never coming into contact with stray gas molecules, never failing for the entire duration of decades-long missions. The longest period of confirmed antimatter storage achieved in any laboratory is approximately 16 hours. To use antimatter for interstellar travel, we would need to scale that storage capability by a factor of tens of thousands, while simultaneously increasing the stored quantities by factors that exceed all production ever achieved. A single failure during launch, during transit, during deceleration, anywhere along the multi-decade timeline, and the spacecraft becomes a brief, brilliant explosion in the void. Antimatter, in other words, is the perfect example of the recurring pattern in interstellar propulsion. The physics works, the mathematics is sound, the principle is established. And yet the engineering implementation remains so far beyond our current capabilities that it occupies a position less like an unbuilt technology and more like a theoretical artifact. It exists on paper. It does not exist in any practical sense. And there is no clear path from where we are now to where we would need to be for it to become real, no roadmap of development, no series of engineering milestones that lead naturally from current capabilities to interstellar antimatter propulsion. We are not behind on the technology. We are not even working on it in any serious sense. The problem is so far removed from anything achievable that no funding agency considers it worth pursuing as a near-term goal. But even if we somehow solved the propulsion problem, even if we conjured up an engine capable of pushing a crude vessel to relativistic velocities and decelerating it again at the destination, we would still face the rest of the journey. And here we encounter a series of challenges that have nothing to do with engines and everything to do with the basic biology of being human in space for decades. Consider what a 40-year mission to Proxima Centauri actually requires of the spacecraft itself. The vessel must be a closed ecosystem, generating its own oxygen, recycling its own water, growing its own food, processing its own waste, repairing its own equipment, and sustaining a human crew through every illness, injury, and emergency that arises across decades of travel. The International Space Station, which receives regular resupply missions from Earth and operates only a few hundred kilometers above the surface, where rescue is at least theoretically possible, has experienced numerous serious failures over its operational lifetime. Cooling system breakdowns, air leaks, computer malfunctions, toilet failures. Each of these has been resolved through ingenuity, replacement parts shipped from below, and the constant attention of mission control teams on the ground. An interstellar spacecraft has none of these advantages. There is no resupply. There is no rescue. There is no replacement equipment except what the vessel carries with it from launch. Every component must be reliable enough to operate for 40 years without external support, or repairable from onboard resources by a small crew that includes everyone who will ever lay hands on the equipment. Closed ecosystems are notoriously difficult to maintain. Earth itself is the only closed ecosystem we know that operates reliably across long timescales, and it does so because it contains an enormous redundancy of biological diversity, vast buffer reserves of water, air, and biomass, and continuous energy input from the sun. A spacecraft cannot replicate this redundancy at full scale. It must compress the entire functioning of an ecosystem into a vessel of reasonable mass and volume. The Biosphere 2 experiment, conducted in the Arizona desert in the early 1990s, attempted to create a sealed closed ecosystem for a human crew of 8 inside a glass-enclosed structure, spanning more than 3 acres. The system suffered cascading failures. Oxygen levels dropped from atmospheric values to levels equivalent to high-altitude mountain peaks, requiring emergency injections of outside air. Carbon dioxide levels fluctuated wildly. Pollinator species went extinct, threatening the food crops. Tensions among the crew became severe. The experiment ran for 2 years and demonstrated that creating a stable, closed ecosystem is far harder than the planners had assumed. We have not made dramatic progress on this problem in the 3 decades since. The basic challenge of sustaining a small group of humans through a self-contained life support system over multi-year timescales remains substantially unsolved. Now extend that challenge across 40 years and add the constraint that the system must function in the unique environment of interstellar space, with cosmic radiation continuously damaging biological tissues and electronic components, with microgravity producing bone loss and muscle atrophy unless artificial gravity is somehow generated, with no possibility of repair from outside, no medical evacuation, no replacement supplies. Every gallon of water lost is gone forever. Every kilogram of food consumed must be replaced from biological production within the vessel. Every spare part used must be remanufactured from raw materials carried at launch. The entire enterprise becomes a balancing act of constraints, where any single significant failure in any single life-critical system could doom the mission. And these are merely the practical challenges. The psychological dimension is, in some ways, even more difficult. Humans are not built for this. Our species evolved over hundreds of thousands of years on the surface of a planet, surrounded by varied environments, social groups of dozens to hundreds of individuals, exposure to natural cycles of light and weather, the constant possibility of new experiences and new encounters. None of that exists in a spacecraft crossing interstellar space. The crew sees the same faces every day, walks the same corridors, eats the same recycled food, breathes the same recycled air. The view outside the windows changes only at glacial pace. Earth becomes a memory, then a distant point of light, then nothing visible at all. The destination is so far ahead that for years, perhaps decades, it remains imperceptible against the background of stars. The crew exists in a tiny pocket of warmth and air, surrounded by infinite cold and emptiness, with no possibility of going outside, no possibility of returning, no possibility of any change to the routine for as long as the journey lasts. Studies of human behavior in isolated environments give us hints about what would happen, none of them encouraging. Antarctic research stations, where small crews spend months together in confinement during the polar winter, regularly produce psychological crises. Submarines, where crews spend months underwater in tight quarters, generate similar problems. The Russian space program conducted long-duration isolation experiments on the ground, sealing crews in mock spacecraft for extended periods to study the psychological effects. The longest of these experiments, called Mars 500, kept a crew of 6 men sealed in a simulator for 520 days, the time it would take to reach Mars and return. The experiment was considered a success in that no catastrophic interpersonal failures occurred, but it required an enormous amount of psychological preparation, careful crew selection, and continuous support from outside experts. And 520 days is roughly 1/40th of the duration of a Proxima Centauri mission. We have no data on what happens to humans confined in the same small space for 40 years, because we have never come close to running such an experiment. What we do know is that human social structures degrade under prolonged isolation and stress. Conflicts that would be trivial in normal circumstances become magnified. Personal habits that seemed quirky at first become unbearable. Cliques form. Resentments build. Romantic relationships develop, end badly, and continue affecting the work environment because there is no possibility of separation. Some crew members withdraw. Some become aggressive. Some develop psychiatric conditions that require treatment. On Earth, treatment means professional psychiatric care, medication adjusted by experts, possibly removal to a different environment. On an interstellar spacecraft, none of these options exist. The crew must handle every psychological emergency themselves, with whatever pharmaceutical resources they brought from Earth and whatever expertise the medical officer happens to possess. And that medical officer, if there is only one, may themselves become the patient. There is no backup, there is no specialist a few hours away. There is only the crew, alone, for decades. Mortality during the journey is statistically certain over 40 years. If you launch a crew of 50 humans in their 30s, some of them will die before arrival. Heart attacks, strokes, cancer, accidents. The natural attrition of any group of 50 people over 4 decades. The mission planning must account for this. Bodies must be handled somehow, either preserved, ejected into space, or processed for nutrient recovery in the closed ecosystem. The survivors must continue functioning despite losing crewmates who were probably both colleagues and close personal contacts. Children may be born during the journey, raising profound ethical questions about whether it is acceptable to bring people into existence whose entire lives will be spent on a spacecraft, who will never know Earth except as videos and stories, who will arrive at a destination they did not choose and were not asked to consent to. These children will need education. They will need socialization with peers, except their peers will be limited to whoever else was born on the journey. They will reach adulthood inside the vessel, take over from the original crew as those originals age and die, and continue the mission as a multi-generational endeavor whose participants increasingly have no memory of the world that launched them. This is what physics demands of any human attempt to reach the nearest star, using even the most optimistic propulsion technologies we can currently imagine. 40 years minimum for the journey itself, possibly much longer. A closed ecosystem operating reliably for that entire span. A psychological environment that no human has ever endured for anything close to that duration. A medical situation in which there is no rescue, no resupply, no specialist beyond what is on board. Mortality during the trip. Births during the trip. The slow conversion of the spacecraft from a vehicle on a mission into a tiny civilization sustaining itself in deep interstellar space, with all the political, social, and personal complications that any human society generates, compressed into a single small vessel from which there is no escape. Some of these challenges might be partially addressed by suspended animation, a technology that has been promised by science fiction for over a century and never delivered by science fact. The idea is that crew members could be placed into a deep state of metabolic reduction, perhaps cooling their bodies to temperatures where biological processes nearly stop, then revived at the destination after the bulk of the journey has passed. Some animals achieve something like this through hibernation, surviving months of reduced activity at lower body temperatures. A few have demonstrated revival after partial freezing. Human suspended animation, however, remains entirely speculative. We have no proven technology that can reduce a human body to deep hibernation and revive it intact. Cryonic preservation, where bodies are frozen at extremely low temperatures after death, has never produced a successful revival of any subject. The technology is regularly portrayed in fiction as solved or near solved, but in actual laboratories it remains a dream rather than a capability. And even if some form of suspended animation were eventually developed, the technical challenges are enormous. The hibernation system itself must operate reliably for decades. The revival process must work without complications. The crew must somehow handle the period before and after their hibernation, including the boring middle years when the spacecraft is just coasting through interstellar space and human attention is required only for emergencies. Suspended animation might solve the psychological problem of confinement by simply removing the experience of confinement, but it does not solve any of the other problems of long-duration spaceflight. And let us assume, optimistically, that all of these obstacles are somehow overcome. The propulsion is built. The closed ecosystem functions reliably. The crew is psychologically resilient and technically expert. The journey lasts 40 years. The crew survives more or less intact. The spacecraft decelerates successfully into the Alpha Centauri system. Now what? What awaits them at their destination? This question is rarely asked seriously. because the journey itself is already so daunting that the destination becomes almost an afterthought. But the destination matters enormously, because everything that has been sacrificed, every year of life spent in transit, every resource consumed by the mission, has been spent in pursuit of arriving somewhere worth arriving. And the available evidence suggests that Alpha Centauri may not be worth arriving at least not in any sense that justifies the cost of getting there. Proxima Centauri b, the most discussed potential destination at our nearest stellar neighbor, was discovered in 2016 through radial velocity measurements that detected the gravitational tug of the planet on its parent star. It is roughly Earth-sized, possibly slightly more massive, and it orbits within the theoretical habitable zone of Proxima Centauri, the band of orbital distances where liquid water could potentially exist on a rocky surface given the right conditions. This sounds promising until you examine the details. Proxima Centauri is a red dwarf, much smaller and cooler than the Sun, emitting less than 1% of the Sun's total light output. To be in the habitable zone of such a dim star, Proxima b must orbit very close, roughly 5% of the distance from Earth to the Sun. Its orbital period is just over 11 days. At that distance, the planet is almost certainly tidally locked, meaning one hemisphere always faces the star while the other always faces away. The day side would be permanently sunlit, the night side permanently dark, with conditions that vary dramatically across the boundary between them. Liquid water, if it exists, could be confined to a narrow band around the terminator, the perpetual twilight zone separating eternal day from eternal night. Tidal locking is not the most serious problem. Red dwarf stars are notoriously violent in their early lives, producing flares that can be hundreds of times more energetic than anything our Sun has ever produced. A planet orbiting close enough to a red dwarf to be in the habitable zone is also close enough to be repeatedly bathed in radiation that would strip away atmospheres, sterilize surfaces, and destroy any biology that had managed to develop. Proxima Centauri is an active flare star. Observations have detected powerful flares with regularity. Whatever atmosphere Proxima b once had may have been long since stripped away by these stellar outbursts. If it retains any atmosphere at all, the surface would be regularly bombarded by radiation that would make Earth's worst geomagnetic storms look like gentle breezes. The conditions on Proxima b, after a 4-decade journey at relativistic velocities, may turn out to be those of a lifeless, irradiated, atmosphereless rock, not significantly more habitable than the surface of Mercury. Alpha Centauri A and B, the Sun-like stars of the binary pair, might host more hospitable planets, but their close orbital embrace makes long-term stable planetary orbits problematic in many configurations. Astronomers have not yet conclusively detected planets around either star, though detection campaigns continue. Even if Earth-like worlds exist around Alpha Centauri A or B, we would not know with confidence what they look like until we arrived. The information we can gather from 40 trillion kilometers away is fundamentally limited. Spectroscopic analysis of any planet's atmosphere can only tell us so much about surface conditions, native chemistry, the presence or absence of liquid water, the existence of life. We could send a mission across decades of space, sacrifice enormous resources and human lives, and arrive at a destination that turns out to be fundamentally inhospitable, a barren rock that cannot support the kind of exploration or settlement that justified the journey. The crew would have committed their lives, the civilization would have committed its resources, and the answer to the question of whether the trip was worth it would be a resounding no. Even an apparently habitable world might present problems we cannot anticipate from across light years. Atmospheric chemistry, incompatible with human biology, surface microbial populations that consume or are consumed by Earth biology in dangerous ways, geological instability, unexpected radiation environments, native ecosystems we cannot enter without destroying. The list of ways an alien world could be subtly or grossly hostile to human visitors is essentially unlimited. We have only one example of a habitable planet in the entire universe to reason from, and that planet is the one we are trying to leave. Generalizing from a sample size of 1 to predict what conditions await us light years away is an exercise in optimism that the universe has no obligation to validate. There is a deeper question lurking here, one that the popular framing of interstellar travel almost never addresses. Why are we so confident that the nearest star system contains anywhere worth visiting at all? The default assumption in most discussions of interstellar travel is that, of course, we want to go there, of course there is something to find, of course the trip will be worth it. But this is a cultural assumption rather than a scientific one. The vast majority of stellar systems we have observed do not appear to contain anything resembling Earth. Most planets that have been cataloged are either gas giants, scorching hot worlds orbiting too close to their stars, frozen rocks orbiting too far, tidally locked planets around dim red dwarfs, or worlds with atmospheres dominated by gases that would suffocate or poison terrestrial biology. Earth-like conditions, with liquid water, breathable atmosphere, moderate temperatures, magnetic shielding, and stable geology over geological timescales appear to be statistically rare. The chance that any specific destination, including the closest stellar systems to our own, contains anywhere a human could actually live without immense artificial life support is small. Even for purely scientific exploration, the question of whether the nearest star contains targets worth a 4-decade journey is genuinely open. Now bring all of these considerations together. The physics demands enormous energies that may exceed anything our civilization can produce. The propulsion technologies that could in principle access those energies remain decades or centuries from realization, with many of them facing fundamental obstacles that may never be overcome. The interstellar medium presents lethal hazards to any vessel traveling fast enough to make the trip in human lifetimes. The biology of being human in confinement for decades has never been tested at the relevant durations and may produce psychological and medical failures that no amount of preparation can prevent. The destinations themselves may turn out to be hostile, lifeless, or merely uninteresting, providing no reward proportional to the cost of arrival. Each of these obstacles, taken individually, would be enough to give serious pause to any mission planner. Taken collectively, they form a wall so high that the question is no longer how we will overcome them, but whether they can be overcome at all by any species operating within the constraints of physics as we currently understand it. This is what I mean when I say that reaching the nearest star may be physically impossible. Not impossible in the trivial sense that we have not done it yet. Impossible in the deep sense that the universe seems to have arranged itself to prevent any biological civilization from spreading easily between the stars. The energy requirements are too high. The distances are too vast. The timescales are too long. The hazards are too severe. The destinations are too uncertain. The obstacles compound on one another in ways that no single technological breakthrough can resolve. We are not one invention away from interstellar travel. We are not 10 inventions away. We may be no inventions at all, away from a permanent, unbreakable confinement to the solar system that gave us birth. This conclusion is uncomfortable for those who have grown up on a steady diet of science fiction promising warp drives in hyperspace and effortless interstellar empires. It is uncomfortable for those who believe in an inevitable expansion of human civilization across the galaxy. It is uncomfortable for anyone who has looked up at the night sky and felt the call of the stars, that ancient pull toward the points of light scattered across the dark, that sense that surely a species capable of building cities and computers and spacecraft must eventually be able to cross the empty distances and walk on the surface of an alien world. The discomfort is understandable, but discomfort is not a refutation. The universe is not obligated to accommodate our preferences. Physics does not consult our hopes when it sets the speed of light, the rocket equation, the energy density of fuels, or the density of the interstellar medium. The constraints exist whether we acknowledge them or not. And yet, the picture I have drawn so far is not the entire picture, because there is one possibility I have not fully explored, one approach that does not require defeating any of the obstacles I have described, one strategy that has occupied serious thinkers for decades and remains technically feasible within our current understanding of physics, even if the engineering is beyond us. The generation ship. The slow, patient, multi-decade or multi-century vessel that does not try to compress the journey through relativistic velocity but instead embraces the enormity of the trip, carrying along not just a crew but an entire small society, multiple generations of humans who will live and die and be born on board, a civilization in transit. The generation ship sidesteps the energy problem by traveling slowly. It accepts that the original crew will never reach the destination. It transforms the question of interstellar travel from a mission to be completed within human lifetimes into a multi-generational project that may take centuries to conclude. it changes the entire framework. And whether such a project is even theoretically possible, whether human civilization can sustain itself in a closed vessel for centuries, whether the descendants of the original crew will still want to complete a mission their great-grandparents started, opens up questions even more profound than the technical obstacles I have been describing. Because if the only way to reach the nearest star is to send forward an entire civilization across centuries of space and time, then the question becomes not just whether we can do it, but what kind of beings would arrive at the other end, and whether they would even still be human in any sense that the people who launched them would recognize. The concept of a generation ship has appeared in serious scientific literature since the 1920s, when the Russian rocket pioneer Konstantin Tsiolkovsky, the same man whose equation traps chemical rockets, also envisioned the possibility of cosmic arcs carrying humanity outward across centuries-long voyages. The basic premise is straightforward in concept and terrifying in implication. You build a vessel large enough to function as a small, self-contained world. You launch it at velocities achievable with realistic propulsion, perhaps a few % of light speed at most, possibly less. You accept that the journey will take centuries. You staff the vessel with a population large enough to sustain genetic diversity and social functioning across many generations. The original crew lives, ages, and dies in transit. Their children are born on board, grow up, have children of their own, age, and die. The grandchildren and great-grandchildren continue the journey. Eventually, after 20 or 30 generations, perhaps more, the descendants of the original crew arrive at the destination, complete the mission their ancestors began, and step out onto a world that no human alive remembers leaving Earth for. This approach genuinely sidesteps the energy problem. At 1% of light speed, the journey to Proxima Centauri takes about 425 years. At 1/10 of 1% of light speed, it takes 250 years. Neither of these velocities requires the cosmic scale energies demanded by relativistic propulsion. Both are within the theoretical reach of fusion drives, advanced ion propulsion, or sustained nuclear pulse propulsion using technology that is within an order of magnitude of what we already understand. The propulsion challenge becomes manageable. The interstellar medium hazards drop precipitously because the kinetic energy of impact scales with velocity squared. At 1% of light speed, hydrogen atom impacts deliver 100 times less energy than at 10% and 1,000 times less than at 30%. Shielding becomes feasible. Radiation exposure becomes manageable. The energy demands of the mission collapse from cosmic absurdity into something a sufficiently committed civilization might actually achieve. But the human problem expands. Now you are asking not whether a single crew can survive 40 years of confinement. You are asking whether a small society of perhaps a few thousand humans can sustain itself for centuries inside a metal hull, generation after generation, without losing the technical knowledge required to operate the spacecraft, without succumbing to civil war or revolution, without the descendants deciding that the entire mission is pointless and refusing to continue, without the ecosystem collapsing, without the genetic diversity becoming insufficient to sustain a healthy population, without any of 1,000 other possible catastrophes that could end the journey somewhere in deep space, leaving a silent vessel drifting forever between the stars with whatever remains of its. The biological challenges alone are formidable. A generation ship must carry a founding population large enough to sustain genetic diversity across many generations of reproduction. Estimates of the minimum viable population vary, but most studies suggest at least several hundred individuals are necessary to avoid inbreeding depression and maintain sufficient genetic variation. Some analyses argue for several thousand. The vessel must accommodate this population along with all the resources required to sustain them, including food production capacity, water recycling, atmospheric maintenance, and waste processing. The ship's mass scales accordingly. Whatever propulsion system pushes, it must accelerate this enormous mass to interstellar velocities, which pushes the energy requirements back up toward the limits we encountered with smaller, faster missions. The vessel must be vast, perhaps larger than any ship humans have ever built, possibly larger than most cities. It becomes a constructed asteroid, a hollowed-out world traveling between the stars at glacial cosmic pace. The political problems may be more difficult than the engineering ones. Imagine you are part of the original crew. You have volunteered for a mission whose purpose you understand, whose value you accept, whose sacrifices you have agreed to endure. You will spend the rest of your life on the vessel. You will not arrive. You will die in transit knowing that your descendants will continue the mission. But your descendants did not volunteer. They did not consent to be born into a confined metal vessel hurtling between stars on a mission they did not choose. They simply exist, products of decisions made before their conception, embedded in a system that gives them no realistic option to leave. By what right do you commit them to this fate? By what mechanism do you ensure that they will continue the mission rather than turning around, slowing down, settling into a stable orbit somewhere in interstellar space, abandoning the destination, or whatever other decisions a future generation might prefer? You cannot give them informed consent before their birth. You cannot enforce your will across generations once you are dead. You can only design the vessel and its institutions in ways that you hope will sustain the mission, knowing that your hope is not a guarantee, and the institutions themselves face pressures that no human society has ever endured. A generationship is the ultimate closed political system, with no external check on internal power. Whatever social structure you launch with must function for centuries, evolving in ways you cannot predict, governed by people you will never meet. Authoritarian structures may consolidate and become tyrannical. Democratic structures may fragment into factions and gridlock. Either failure mode could be fatal to the mission. A civil war on a generation ship is a civil war inside a fragile life support system. Even minor damage to critical equipment during such a conflict could doom the entire population. Religious schisms, political revolutions, generational conflicts, ideological disputes, all of these are inevitable in any human society over centuries. On Earth, they cause suffering but rarely threaten the continuation of the species. On a generation ship, they could end everything. The technical knowledge required to operate the vessel must also be transmitted across generations without degradation. The crew that arrives at the destination must be capable of decelerating the ship, navigating the approach, performing emergency repairs, and conducting whatever exploration the mission requires. They must be educated in fields like medicine, engineering, biology, and physics to standards that may not exist on the ship's home planet by the time they arrive. They must train themselves on equipment they have never seen used in normal operation because the equipment has been operating continuously for centuries during their lifetimes and the lifetimes of their parents and grandparents. They must maintain literacy in technical disciplines whose original purpose was the planning and execution of a mission already partially complete. The risk that important knowledge will be lost, garbled, or transformed into something useless across so many generations is enormous. Cultural drift is not a possibility. It is a certainty. The question is only whether the drift will be compatible with the mission's continued execution. Communication with Earth across these centuries adds another layer of complication. By the time the descendants of the original crew arrive at Proxima Centauri, the civilization that launched them may no longer exist in any recognizable form. 400 years is a span longer than the United States has existed as a nation. It is longer than the lifetime of most political states in human history. The institutions, governments, languages, and cultures that sponsored the mission may have collapsed, transformed, or been replaced before the ship reaches its destination. Whatever message the crew prepared to send back upon arrival may arrive at a planet that no longer cares, or no longer remembers the mission, or no longer possesses the technology to receive the signal. The crew will have spent 20 generations completing a journey for an audience that may no longer exist. They will arrive as ambassadors to a destination from a civilization that may have vanished into history. And what if the destination, after all of this, after all the generations and all the sacrifices and all the slow-grinding centuries of confinement, turns out to be uninhabitable? What if the spectroscopic analyses we conducted before launch were wrong, or incomplete, or irrelevant? What if the surface conditions on the destination world prove fatal to humans? What if the local microbiology cannot coexist with terrestrial life? What if there is no microbiology at all, just a sterile rock that cannot support the kind of settlement the mission was designed to establish? The arriving generation cannot turn around. They cannot return to Earth. The vessel, if it has consumed its propellant on deceleration, may not have the fuel for another long journey. They are stranded, perhaps permanently, in a stellar system that offers them nothing they can use. Their descendants, if there are any, must figure out how to survive in their hollow vessel, orbiting a hostile world for as long as the life support systems function, and then die when the systems fail. This is the optimistic scenario for generation ships. The pessimistic scenarios are darker. Every long human endeavor has experienced failure modes that the planners did not anticipate, and there is no reason to think that interstellar generation ships would be exempt. The mission could end at any point along the way, and depending on when the failure occurs, the consequences could range from the merely tragic to the unspeakably horrific. A slow degradation of the closed ecosystem, perhaps caused by accumulated genetic damage from cosmic radiation, or by the gradual depletion of essential elements that cannot be perfectly recycled, could leave the population struggling to feed itself for decades before any final collapse. A breakdown of social order could leave survivors locked in protracted conflict aboard a vessel they no longer have the cooperative capacity to maintain. A failure of fertility or genetic diversity could mean that one generation is the last, that no children are born, that the ship arrives at its destination as a sealed coffin. Any of these outcomes is possible. None of them can be reliably prevented from across decades or centuries of distance, because the mission, once launched, cannot be helped from outside. There are alternative approaches that try to bypass the human problem entirely. One is the digital uploading scenario, where rather than sending biological humans, you send the recorded consciousness of those humans encoded in some computational substrate. The advantages are enormous. A digital consciousness does not require food, water, oxygen, or psychological care. It can be paused for the duration of the journey and reactivated at the destination with no subjective experience of the trip. It can be compressed, replicated, and transmitted in ways that biological humans cannot. The mass of the spacecraft drops by orders of magnitude. The energy requirements collapse correspondingly. A small probe carrying digital copies of human minds could conceivably reach Proxima Centauri at relativistic velocity within decades, with the uploaded consciousnesses experiencing nothing during the trip and waking, in some sense, at the destination. The problem is that we have no idea how to upload a human consciousness. We do not know what consciousness is at the level of physical implementation, or whether it can be transferred from biological neurons to artificial substrates without losing the essential properties that make it consciousness in the first place. The most optimistic projections of when such technology might become available are speculative to the point of fantasy. We have no demonstrated capability to map a human brain at the resolution required, let alone to recreate that mapping in functional form on a different physical platform. The technology is not behind schedule. It is not partially developed. It is not at the prototype stage. It does not exist in any meaningful sense, and it may not exist for centuries, if ever. Even those who believe such uploading will eventually become possible cannot point to any concrete path leading from current neuroscience to a working implementation. We are speculating about a technology we do not understand to solve a problem we cannot solve any other way, and the speculation does not become more credible just because we want it to be true. A related approach is the von Neumann probe, named after the mathematician who first formalized the concept. Rather than sending biological humans or digital copies of humans, you send a self-replicating robotic probe. The probe travels to a destination, uses local materials to build copies of itself, and dispatches those copies to other destinations. Over enough generations, a single launched probe could in principle visit every star system in the galaxy. Humans would not personally travel anywhere. We would simply launch the seed of an exploration program that would carry our presence outward across cosmic time, gathering information and transmitting it back to Earth. The probes themselves would not need to address the biological challenges of human spaceflight. They would not need closed life support systems. They would not need psychological care or social structures. They would simply need to function, build copies of themselves, and continue the mission across millions of years. The technology for self-replicating probes does not exist either. We can build robotic spacecraft that perform specific tasks. We cannot build machines that, once delivered to a planetary surface, can mine raw materials, refine them into manufacturing inputs, and assemble those inputs into copies of themselves with no human supervision. The components of such a system, robotic mining, automated refining, machine assembly of complex equipment, do exist in primitive forms in terrestrial industry, but no one has demonstrated the integration of these components into a self-sustaining replicating system. Even on Earth, with infinite resources, expert technicians, and continuous supervision, fully autonomous self-replication remains unachieved. Doing it on an alien world, using alien materials, with no possibility of repair or oversight, represents a level of engineering that may again be centuries away if it is achievable at all. What all of these approaches share is that they push the problem of interstellar travel into the future, into technologies that do not yet exist, into capabilities that we cannot currently demonstrate or even confidently predict. The serious answer to the question of how we reach the nearest star, given current technology, is that we do not. We cannot. The propulsion is inadequate, the energy is insufficient, the life support is impossible, the destination is uncertain, the timescales are inhuman, and the failure modes are catastrophic. Every proposed solution either fails on examination or relies on technologies that may never become available. This is what the universe actually looks like when we examine it without the comforting illusions that science fiction provides. This brings us to a question that has haunted serious thinkers about the cosmos for decades. If interstellar travel is so difficult, so close to impossible for biological civilizations operating within physics as we understand it, what does that tell us about the universe itself? About the apparent silence of the cosmos? About the absence of any detectable signs of other intelligent civilizations, despite the existence of hundreds of billions of stars in our galaxy alone, hundreds of billions of galaxies in the observable universe, and timescales of billions of years over which intelligent life could have developed and spread? This is the Fermi paradox, the disturbing observation that the universe should be full of voices and instead appears to be empty. There are many proposed resolutions to the Fermi paradox. Perhaps intelligent life is exceedingly rare. Perhaps it tends to destroy itself before achieving interstellar capability. Perhaps it deliberately conceals itself from external observation. Perhaps it has chosen to remain on its homeworlds rather than expanding outward. But one resolution, often overlooked or dismissed, is simply this. Perhaps interstellar travel is genuinely as difficult as it appears, and no biological civilization can reliably accomplish it. Perhaps every species that arises in the universe finds itself trapped in its home solar system by exactly the same physical constraints that trap us. Perhaps the silence of the cosmos is not evidence of absent civilizations, but evidence of confined civilizations. Each one unable to reach out across the gulf of stars, each one staring at the same impossible distances we are staring at, each one running into the same exponential walls in the rocket equation, the same lethal interstellar medium at relativistic velocities, the same insurmountable energy requirements, the same biological and psychological limits on long-duration confinement. The universe might be full of intelligent species, all of them stuck in their own little patches of warmth around their own ordinary stars, all of them looking up at the same uncrossable distances and reaching the same conclusion we are reaching tonight. This is a deeply unsettling possibility. It suggests that the apparent emptiness of the cosmos may be a permanent feature of intelligent life, rather than an indictment of any particular civilization. It suggests that we are not unique in our isolation, but typical of it. Every intelligent species, no matter how advanced, may face the same wall we face, and the wall may be high enough that no biological civilization ever crosses it. The universe is not filled with empires and federations and galactic civilizations, because the physics does not allow them to form. The fundamental separation between stars is too vast, the energies required to bridge that separation are too great, and the species that arise in any given stellar system find themselves permanently stranded there, gazing outward at the lights of other inhabited worlds they will never reach. If this is true, then humanity's situation is not extraordinary, it is the default. We are not failing to spread among the stars because we are too primitive or insufficiently advanced. We are failing to spread among the stars because the universe does not permit any biological civilization to spread among the stars. The interstellar voyages that fill our science fiction are not future achievements waiting for the right technology. They are mathematical impossibilities dressed in the language of inevitable progress. The galaxy is not waiting for us to come exploring. The galaxy is perhaps full of waiters, none of whom can leave their tables. But there is something deeper still hidden in this conclusion, something that challenges not just our assumptions about space exploration, but our entire framework for thinking about what intelligent life is and what it can do. Because if biological civilizations cannot spread between the stars, then the future of human consciousness, if there is one beyond our home system, may not look anything like what science fiction has trained us to expect. It may not involve human beings visiting alien worlds. It may not involve faster-than-light travel or warp drives or wormholes, or any of the imaginative concepts that have populated our cultural understanding of cosmic exploration. It may instead involve something stranger, something that abandons the project of moving biological humans through interstellar distances and replaces it with the project of moving information, signals, perhaps something like consciousness, across spans of time and space too vast for any organism to traverse. This is the realm of speculation, but the speculation is grounded in the same physics that produces the impossibility I have been describing. If matter cannot be efficiently transported across light years within the lifetime of any organism that uses it, then perhaps the future of intelligence in the universe is not about transporting matter at all. Perhaps it is about transporting patterns. Information can travel at the speed of light. Radio signals from Earth, given a powerful enough transmitter and a sensitive enough receiver, could in principle communicate everything humans know to a civilization on a distant star, in less than the time required for any spacecraft to make the same journey. We could not visit them, but we could speak with them, slowly, across delays of years or decades or centuries, in a kind of cosmic correspondence that would be the only realistic form of contact between intelligent species. Whether any such civilizations exist to listen, we do not know. The Fermi paradox suggests that we have not detected them, but the universe is large, and our search has been limited. What we do know is that this kind of contact, if it ever occurs, will not resemble anything we have imagined when we dreamed of reaching for the stars. There will be no walking on alien soil. There will be no first handshake between species. There will be no exchange of ambassadors or trade delegations or any of the forms of contact that have shaped human civilizations across our own planet. There will be only signals, faint, ancient, slowly arriving across the dark, perhaps so faint that they require decades of observation to detect, perhaps so ancient that the senders are long since extinct, perhaps so different from anything we expect that we cannot even recognize them as messages when they arrive. The cosmos, viewed through the lens of the impossibility of interstellar travel, becomes a different kind of place than the one most people imagine. It is not a vast frontier waiting to be settled. It is not a network of stellar destinations connected by future technologies. It is a great, silent, mostly empty volume in which small pockets of warmth and complexity arise around individual stars, persist for some span of time, and either fade away or eventually go extinct, all without ever meaningfully connecting to one another. Each star system is its own isolated universe, in a sense, separated from all others by distances that no biological inhabitant can cross. The thin shell of warmth and habitability around our sun is essentially the entirety of the cosmos that humans can ever physically reach. Everything beyond that shell is observable but inaccessible, a permanent backdrop of distant lights that we can study from afar but never visit. This conclusion, if accepted, transforms our understanding of what it means to be human, to be alive, to exist as a species capable of looking out at the universe and asking questions about it. We are not aspiring interstellar explorers temporarily confined to our home planet. We are permanent residents of a single solar system, bound here by the same laws of physics that hold every other intelligent species to its own home. The dreams of cosmic expansion that have animated so much of our culture, our science fiction, our long-term planning, may rest on assumptions that the universe simply does not honor. We may have to learn to be at home here, on this planet, around this star, in this small, warm pocket of the cosmos, because the cosmos beyond does not seem to be a place where we can go. This is a sobering thought, but it is not necessarily a depressing one. The pocket of the cosmos that we can reach, the solar system around our sun, is itself enormous compared to anything our species has ever fully explored. There are worlds in our own backyard that we have barely glimpsed. The icy moons of Jupiter and Saturn, with their hidden oceans and possible biospheres. The frozen surfaces of the outer planets, with geological histories we have not begun to read. The asteroid belt, with its millions of remnant fragments from the formation of the solar system. The Kuiper belt, with its scattered icy bodies stretching out to the edge of the planetary region. The Oort cloud, with its trillions of comets in the deep dark beyond. Each of these regions contains more terrain, more chemistry, more potential for discovery than humanity could exhaust in millennia of dedicated exploration. We do not need to leave the solar system to find limitless frontiers. The frontiers within our own system are themselves vast beyond easy comprehension. But the question that opened this discussion remains: why does reaching the nearest star may be physically impossible? And the answer, drawn from everything we have considered so far, is that the universe was not built with our convenience in mind. The distances are too great, the energies too high, the biology too fragile, the timescales too long, the destinations too uncertain. We are pinned to this place, this single warm pocket around this single ordinary star, by the same laws of physics that allow us to exist at all. The same laws that make stars possible, that allow planets to form, that permit chemistry and biology and consciousness, also separate us irrevocably from every other place where similar processes might be occurring. We are not unique in our isolation. We are typical of it. And the cosmos that we have inherited, the cosmos in which we will live out whatever future our species manages to create, is one that consists of one solar system that we can inhabit and an unreachable infinity of other solar systems that we cannot. This does not mean we should not try. Perhaps the interstellar probe that NASA is currently conceiving will fly within our lifetimes and add another layer to our understanding of the boundary between our solar system and the surrounding interstellar medium. Perhaps Breakthrough Starshot or some successor to it will eventually launch tiny probes toward Alpha Centauri and return brief flashes of data from a flyby of our nearest stellar neighbor. Perhaps fusion propulsion, if it ever becomes practical, will give us the capability to send substantial robotic missions to nearby stars over the course of decades or centuries. Each of these accomplishments would be remarkable. Each would expand our knowledge of the cosmos in ways that are difficult to predict. None of them, however, would constitute the kind of human interstellar travel that has been promised by science fiction. None of them would give us the ability to walk on the surface of a planet around another star within the span of a single human life. None of them would break the wall that physics has erected around us. What we may eventually accomplish is something more modest and more profound at the same time. We may learn to be at peace with our cosmic location. We may develop a relationship with the universe that does not require us to physically traverse it in order to know it, study it, or feel ourselves part of it. We may come to understand that the dream of stepping onto worlds around other stars was, perhaps, never a realistic goal, but the dream of understanding those worlds, of mapping them with our telescopes, of analyzing their atmospheres with our spectrometers, of imagining what they might be like and what kinds of life they might harbor, all of that remains entirely within reach. We can know the cosmos without being able to visit it. We can be informed inhabitants of a vast universe without being travelers across it. Consider what we have already accomplished from this single planet. Without ever leaving the solar system in any meaningful sense, we have mapped the surface of every major body in our own system. We have detected over 5,000 confirmed exoplanets orbiting other stars, most of them within the past decade. We have measured the atmospheres of dozens of these worlds, identifying water vapor, carbon dioxide, methane, and other compounds that hint at the chemistry of those distant places. We have observed the merging of black holes through the gravitational waves they sent rippling across the cosmos, billions of years before our existence, finally arriving at instruments built by a species that did not exist when the events occurred. We have detected light from galaxies whose distance places them in the early universe, observing them as they were when the cosmos was only a few 100 million years old. We have measured the cosmic microwave background with such precision that we know the age of the universe to within a few tens of millions of years, the geometry of space to within fractions of a percent, and the proportions of ordinary matter, and dark energy that compose it. All of this we have done from one tiny planet, never leaving our local neighborhood, peering outward with instruments built from the resources of a single solar system. The next century will likely add far more to this picture. Larger telescopes already under construction will be able to directly image planets around nearby stars, potentially identifying biosignatures, the chemical fingerprints of life in their atmospheres. We will know, perhaps within decades, whether the worlds around our nearest stellar neighbors have life on them. We will be able to study those worlds in detail without ever sending a single spacecraft toward them. The information will arrive, as it always has, in the form of light, photons traveling at the speed of light across the gulf of stars, decoded by instruments designed and built on Earth. We will not visit those worlds. We will know them. The distinction matters. And the second is not, perhaps, as inferior to the first as our cultural narratives suggest. There is a kind of dignity in accepting limits we cannot defeat. The history of human civilization is partly the history of pushing against constraints and overcoming them. We learned to fly, we learned to travel underwater, we learned to communicate across oceans and to reach the moon. Each of these accomplishments seemed impossible to earlier generations, and each was eventually achieved. The pattern of crossed limits has shaped our cultural expectation that any limit can eventually be crossed if we work hard enough. But this pattern does not extend to physical laws. Some limits are not engineering challenges. Some limits are written into the structure of reality itself. The speed of light does not yield to ingenuity. The exponential demands of the rocket equation do not soften with cleverness. The energy required to push a substantial object to a substantial fraction of light speed is not negotiable. These constraints will exist for any civilization that arises within the universe we inhabit, no matter how advanced that civilization becomes, no matter how long it has to develop, no matter what resources it can muster. The limits are universal because the laws producing them are universal. Recognizing this is not surrender, it is realism. And realism, properly understood, is the foundation of any genuine accomplishment. We cannot solve a problem by misunderstanding its nature. We cannot achieve interstellar travel by pretending the obstacles are smaller than they are, by hoping that some future technology will overcome physics that stands solidly against it. By dressing our wishes in the language of inevitability, we can, however, achieve a great deal by accurately assessing what is possible and pursuing it with rigor. The frontier we can actually explore is the solar system. The information we can actually gather from the wider cosmos is vast and growing. The intellectual journey we can undertake to understand the universe is essentially limitless, even if the physical journey is constrained. Within these realistic frameworks, there is more than enough for our species to do, more than enough for each of us to participate in, more than enough to give meaning to many lifetimes of work. There is also a strange and quiet beauty in the cosmic situation we find ourselves in. The universe is enormous. Our reach is small. Between these two facts, there is a kind of intimate relationship, a dependence, a gratitude. The same laws that prevent us from reaching the nearest star also gave us the sun. The same physics that traps us here also makes our existence possible. The same cosmic loneliness that surrounds our solar system also defines the preciousness of the small, warm patch in which we live. We did not arrange for this situation. We did not choose to be a species that arose in a cosmos where interstellar travel is essentially impossible. The cosmos was simply what it was, and we evolved within it. And now we are aware of it, and we are facing the question of what to do with that awareness. The answer, perhaps, is to live well in the patch we have. To take care of the only world we can actually inhabit. To value, more than we sometimes do, the planet beneath our feet, the air we breathe, the water we drink, the species with whom we share this one small ecosystem in the vast empty cosmos. If we cannot leave, then we must learn to stay. And staying, done well, can be its own form of greatness. The night sky, when you look at it with this perspective, becomes a different kind of view. Each point of light is not a future destination. Each point of light is a permanent neighbor, separated from us by distances we cannot cross, glowing across the dark to remind us that we are part of a much larger story than our own. The stars are not promises of future expansion. They are companions, witnesses, distant relatives whose existence we share even though we will never meet them. Looking at them is not a preparation for travel. It is its own kind of communion, a reaching outward of attention and awareness, a participation in the cosmos that does not require physical movement. We are connected to the stars in the way an ocean is connected to its coastline. We are bounded by them. They define the shape of our place in the universe. They are present to us in a way that has nothing to do with our ability to reach them. This is the quieter, deeper truth that emerges when we accept the impossibility of interstellar travel. We do not need to reach the nearest star to know that it is there. We do not need to walk on planets around Alpha Centauri to participate in the cosmic order that includes those planets. The participation happens through observation, through understanding, through the long cumulative effort of science to map and comprehend the universe. We are participants whether we travel or not. We are cosmic beings whether we leave our solar system or not. The galaxy does not become more real to us when we visit it. It is already real. It is already there in every direction, surrounding us with hundreds of billions of stars and incalculable wonders, all of which we can study, theorize about, photograph, measure, and imagine, even if we can never touch any of them. There is also a possibility worth considering, one that does not depend on humans physically traveling anywhere, but that could nonetheless extend our presence into the cosmos in some form. The possibility of communication. If other intelligent species exist in our galaxy, even if neither they nor we can travel between stars, we might still be able to talk to one another. Radio signals can cross interstellar distances. Lasers can carry information across light years. A civilization that has reached our level of technology can in principle send messages out into the galaxy, and a civilization at a similar level can in principle receive them. This is the basis of the search for extraterrestrial intelligence, the long-running scientific project that has been listening to the cosmos for decades, hoping to detect a signal that did not come from natural processes, that carries the unmistakable fingerprint of an intelligent sender. So far, we have heard nothing. The galaxy has been silent on every frequency we have searched. Whether this silence reflects an absence of intelligent civilizations, or our limited search capacity, or a deliberate choice by other civilizations not to broadcast, or some combination of these factors, we do not know. But the possibility that contact could occur, even if neither party can travel, remains alive. We could exchange information with another species across interstellar distances, even if we never meet them in person. We could learn about their world, their history, their understanding of the universe, while they learn about ours. The exchange would be slow. A single round-trip conversation between Earth and Proxima Centauri would take roughly 8.5 years. With more distant correspondence, the delays would extend to decades or centuries. But information could flow. Knowledge could be shared. Whatever else interstellar travel might mean, the meeting of minds across cosmic distances does not require any physical journey at all. If we ever do detect a signal from another civilization, the impact on our species would be profound, and it would be entirely independent of any ability to visit the senders. The mere knowledge that we are not alone, that the universe has produced intelligent life more than once, would change our cultural and philosophical landscape forever. We would learn that the cosmos is the kind of place where minds emerge, where curiosity arises, where some species build instruments to listen for signals from other species. We would learn this without traveling anywhere. The discovery would happen on Earth, made by instruments built on Earth, processed by computers built on Earth, interpreted by scientists who never left Earth. The cosmic context would expand, even though our physical reach remained the same. This may, in the end, be the kind of contact the universe permits: communication without travel, knowledge without visit, companionship across distances that no physical body can cross. It is not the future that science fiction trained us to expect, but it is a future that the actual physics of our universe could conceivably allow. And it would be a meaningful future, one in which our isolation is partially broken even though our confinement persists. We would still be unable to reach the nearest star. We would simply be talking to whoever is there. But if no one is there, if the silence we have observed continues, if our search ultimately reveals that the galaxy is empty of intelligent life, or that whatever life exists is not interested in or capable of communication, then we are alone in a deeper sense than we may yet have appreciated. We are not just the only intelligent species we know of. We may be the only intelligent species that exists in any region we can plausibly contact. Our solar system is not just our home. It is the entirety of the cosmos that contains beings like us. The vast remainder of the universe, the trillions of stars, the hundreds of billions of galaxies, the unimaginable expanses of space and time, all of it stretches out around us as a magnificent backdrop that we can study but cannot share with anyone because there is no one else to share it with. The cosmos becomes our private theater. We are the only audience, watching alone as the universe performs its enormous slow play of stellar formation, galactic evolution, and cosmic expansion. There is no one to talk to about what we see. There is only us, alone with our observations, alone with our understanding, alone with the questions we ask and the answers we tentatively construct. This solitude, if it is the truth of our situation, has both terrible and beautiful aspects. The terrible aspect is the loneliness. We arose in a universe so vast that it could contain billions of civilizations, and yet we may be the only one. Or we may be one of millions. all separated from one another by distances that ensure none of us ever knows the others exist. Either possibility involves a kind of cosmic isolation that no human society has ever fully confronted. We are used to the idea that there are other people somewhere, even if we have not met them, even if they live in cultures we do not understand, even if they are separated from us by oceans and continents. The possibility of being alone in the universe, of being the only consciousness in a cosmos otherwise filled with empty matter and lifeless processes, is a possibility our cultural frameworks have not adequately processed. The beautiful aspect is the responsibility. If we are alone, or even if we are merely effectively alone because of the impossibility of reaching anyone else, then we carry the only intelligent observation of the cosmos that exists in our portion of the universe. We are the eyes through which the cosmos sees itself, here. Our consciousness is the local instance of consciousness. Our questions are the only questions being asked in any region we can influence. This places upon us a kind of stewardship that no other framing of our cosmic situation captures. We are not insignificant specks in a cosmos teeming with life. We are, perhaps, the local representatives of consciousness itself, charged by our position with whatever meaning consciousness can give to the universe by being aware of it. The cosmos does not need us. But our awareness of the cosmos is, in some sense, the only awareness the cosmos has of itself. Here, in this region, at this time, whatever value we assign to that awareness, whatever care we take to preserve and develop and refine it, has cosmic significance simply because there is nothing else to compare it to. This is a heavy weight to carry. It is also, in its way, an extraordinary privilege. The species that arises in a vast, empty cosmos and discovers that it cannot leave its home star is a species placed in a unique position. It must come to terms with its own boundaries. It must decide what to do with the consciousness it has been granted within the small space it has been granted. It must build, within the confines of one solar system, whatever future it is going to have. This is not a failure mode. It is simply the situation. The species that lives in this situation can choose to live well, to develop its understanding, to take care of its home, to extend its observations as far as physics permits, to ask the questions that need asking, to build the instruments that need building, and to leave whatever record it can of having existed and tried and learned. The fact that none of this involves walking on alien soil does not diminish its significance. The fact that all of it happens within a single solar system does not make it small. When we look up at the night sky, then, we are looking at a world we will never visit but can spend our entire lives studying. We are looking at lights that have traveled for years or centuries or millennia to reach our eyes, carrying information about places that existed when those lights were emitted but may have changed dramatically by the time the lights arrived. We are looking at a frozen image of the cosmos, a slice through cosmic time, all of it coming to us across the same medium that prevents us from going to it. The light is the only contact we will ever have with most of what is out there. And the light is enough. It carries everything we can learn about those distant places. It is the messenger we receive without ever sending one of our own. The universe speaks to us through photons even though we cannot speak back through anything that travels. There is a kind of conversation in this, even though it is one-sided. Stars sending us their light, dying long before we receive it, leaving behind only the slow procession of photons that finally arrive at our telescopes and our retinas. Galaxies broadcasting their existence across spans of time that dwarf our entire civilization. The cosmic microwave background suffusing every direction with its faint glow, the afterimage of the early universe still detectable to instruments sensitive enough to listen for it. All of this comes to us, fills us, informs us. Even though we send nothing comparable in return, we are listeners in an ancient cosmos. We are receivers of signals we did not transmit. The conversation, if it is a conversation, runs in only one direction. The cosmos speaks, we listen. And our listening, our understanding, our incorporation of the cosmic data into the framework of human knowledge is the only response we can offer. That response, taken seriously, is enough to fill many lifetimes. The work of listening to the universe, of decoding its signals, of building theories that encompass what we observe, of asking new questions and developing new instruments to address them, is an endless project. There is no point at which we will know everything. There is no edge of cosmic ignorance that we will eventually reach and then have nothing more to do. The universe is too large and too complex for our understanding ever to be complete. We will always be partway through learning. And every generation will inherit the partial understanding of the previous generation, and add to it, refine it, sometimes overturn it, always extending it. The species that cannot leave its solar system has more than enough to do for as long as it persists, as long as it chooses to continue the work of comprehending the cosmos in which it finds itself. So when we ask whether reaching the nearest star may be physically impossible, the answer that emerges from honest examination of physics and engineering is that yes, it probably is, in any sense that matches our cultural expectations of interstellar travel. Crewed missions to other star systems completed within human lifetimes, returning travelers who have walked on alien worlds and returned to share what they saw with the civilization that sent them. This is likely beyond the reach of any biological civilization operating within our universe. Robotic flybys at relativistic velocities, sending back brief glimpses of nearby stars, may eventually be achievable. Slow generation ships transporting small civilizations across centuries of travel may be theoretically possible if we are willing to accept the enormous costs and unknown risks they involve. Communication with other civilizations, if any exist, may be achievable across timescales of years or decades or centuries, with information flowing slowly between worlds whose inhabitants will never meet. But the dream of becoming a galactic civilization, of spreading across the stars, of building a cosmic empire connected by faster-than-light travel and easy interstellar commerce, this dream appears to be incompatible with the physics of our universe. The cosmos was not built to permit such expansion. The energies are too high, the distances too great, the timescales too long, the biological constraints too severe. We are stuck. We will likely always be stuck. And our future, whatever shape it takes, will most likely unfold within the boundaries of our home solar system, surrounded by a cosmos we can study but cannot enter. This may sound like a bleak conclusion. It is, perhaps, only bleak if you measured success by the wrong metric. The metric of interstellar conquest is not the metric the universe offers us. The universe offers us, instead, the metric of cosmic understanding within a fixed location. It offers us the possibility of being a species that learns deeply about a vast cosmos from one tiny vantage point. It offers us the possibility of caring well for the only world we can actually inhabit. It offers us the possibility of building a long, stable civilization that does not depend on continuous expansion for its survival. These are different goals than the ones science fiction trained us to pursue, but they are not lesser goals. They are simply the goals that match the universe we actually live in, rather than the one we sometimes imagine. There is a particular kind of maturity in accepting this. The maturity of a species that recognizes its limits and chooses to work within them. The maturity of a civilization that does not need to colonize the stars in order to feel that its existence is meaningful. The maturity of a consciousness that can look out at the vast cosmos, understand that almost all of it is permanently beyond its reach, and feel not despair, but appreciation. The cosmos does not owe us anything. It does not owe us the ability to traverse it. The fact that we exist at all, that we have evolved consciousness capable of asking these questions, that we live in a universe complex enough to support the kind of understanding we are pursuing, is itself a remarkable circumstance. We are not entitled to interstellar travel. We are, however, the beneficiaries of a cosmos that allowed us to come into being, and our gratitude for that, properly cultivated, is more than adequate compensation for the limits we cannot break. The nearest star is 4.24 light-years away. It will remain that distance for as long as the cosmos retains its current configuration. Light from Proxima Centauri, leaving its surface tonight, will arrive at Earth in just over 4 years, carrying information about a world we will probably never visit. A spacecraft launched tonight at any propulsion technology we currently possess will not reach that star within any human timescale. A spacecraft launched in any technology we can clearly project for the coming centuries will, at best, arrive after generations of effort and consume resources comparable to the entire output of our civilization. The wall is high, the wall is real, the wall may be permanent, and yet we will continue to look up at the southern sky when we have the chance, and find the place where Alpha Centauri sits among the constellations of the southern hemisphere. We will continue to point our telescopes at it, gather its light, analyze its planets, learn what we can about a system we cannot visit. We will continue to build slightly better instruments, slightly more sensitive detectors, slightly more powerful computational tools to process the data those instruments return. We will continue to expand our understanding of the cosmos, even as our physical presence within it remains essentially fixed. This is what we can do. This is what we are doing. This is, perhaps, what intelligent species generally do throughout whatever portion of the universe they inhabit. They reach as far as they can with their understanding, even when they cannot reach with their bodies. They learn what they can about the unreachable, even though the learning never converts into visiting. They become cosmic beings through awareness, rather than through travel. Tonight, somewhere overhead, the photons that left Proxima Centauri 4 years and 3 months ago are arriving at Earth. They have been traveling through interstellar space for that entire span. They have crossed the helipause that Voyager probed. They have passed through the interstellar medium that those probes measured. They have moved across distances that no spacecraft we have ever built has come close to traversing. And now they arrive here, at the surface of our planet, where some of them will be detected by telescopes and recorded by instruments and added to the slow, patient archive of human astronomical knowledge. The star we cannot reach has reached us in the only form that interstellar communication is allowed by physics. It has spoken to us through its light. We have listened. The conversation continues. Whether it ever extends beyond this, whether we ever do anything more than listen, whether some future generation finds a way around the walls I have described in this exploration tonight, none of us can know with certainty. What we can know is the situation as it currently appears, the limits as they currently stand, the picture that physics paints when we look at it without the comforting filters of fiction. The picture is sobering. The picture is also, in its way, complete. It tells us where we are, what we can do, what we probably cannot do, and what kind of cosmos we inhabit. The picture does not tell us how to feel about it. That part is up to us. Thank you for joining me tonight on this difficult journey. We have looked at the physical reasons why reaching the nearest star may be more than just hard. We have explored the rocket equation, the energy demands of relativistic travel, the lethal nature of the interstellar medium at high velocities, the biological limits of human confinement, the uncertain destinations that may or may not reward our arrival, the multi-generational sacrifices that any actual mission would require, and the deep philosophical implications of accepting that the cosmos may not permit any biological species to spread between the stars. None of this is a conclusion I take pleasure in delivering. I would prefer, like most people who love space, to live in a universe where interstellar travel is achievable, where humanity's future includes journeys to other suns, where the night sky is not just a panorama of distant lights but a map of future destinations. I do not, however, get to choose the universe I inhabit. Neither do you. Neither does our species. We get only to confront what is, as honestly as we can, and to find within that honest confrontation whatever meaning, beauty, and purpose we are able to construct. If this kind of deep, uncomfortable, but genuinely curious exploration of the cosmos resonates with you, please take a moment to like this video and to subscribe to the channel. Deep space signals exists because there are people in the world who would rather face the universe as it actually is than as we might wish it to be, and your support is what allows me to continue making these long, careful, honest explorations of what we know and what we do not. The next time you find yourself outside on a clear night, look up and find a bright point of light. Anyone will do, and remember that what you are seeing left its source years or decades or centuries ago, that the photons entering your eye have crossed gulfs of space no spacecraft will ever cross, that the light has come to you because the universe permits light to travel even when it does not permit you to. You are receiving a message. The message is the cosmos, telling you that it exists, that it is enormous, that it is mostly empty, that the warm pockets of structure within it are rare and precious, that you are one such pocket, that your awareness is a strange and unlikely development in a universe that is mostly cold and dark. The message does not tell you what to do with this information. That is for you to decide. The nearest star will not become reachable in your lifetime. It will not become reachable in your children's lifetimes. It may not become reachable ever for any descendant of yours, for any future iteration of our species, for any consciousness arising within our solar system. This is not a tragedy. This is simply the universe. And the universe, taken on its own terms, contains more than enough beauty and mystery and meaning to fill our existence here, on this small planet, in this single solar system, surrounded by an unreachable infinity that we can nonetheless study, contemplate, and love. Sleep well tonight, beneath the stars that you will never visit. They are watching over you, in their distant, indifferent way, just as they have watched over every human who has ever lived and looked up. You are part of an old story. The story is set on this earth, around this sun, and it is the only story we are likely to ever inhabit. Let it be enough. Let the cosmos out there remain out there. And let us continue here, doing what we can with what we have, for as long as we have the privilege of being conscious in a cosmos that mostly is not. Good night, and may the unreachable stars give you the same quiet wonder they have given me. But before you drift off tonight, there is one more thought I want to leave with you, because I do not want this exploration to end on a note of pure resignation. The picture I have painted across these hours is honest as I can make it within the limits of what we currently understand. The walls between us and the nearest star are real. The propulsion problems are real. The energy demands are real. The biological constraints are real. The destinations may or may not be worth arriving at. All of this is true. But truth is rarely the whole story when it comes to long futures and the species that inhabit them. Truth tells us where we are. It does not tell us where we will end up. And the difference between those two things is the space in which all of human possibility unfolds. A century ago, the idea that we would land machines on Mars, photograph the surface of Pluto, fly probes through the rings of Saturn, and listen to the echo of the Big Bang from satellites parked at gravitational balance points beyond the moon would have seemed nearly as extravagant as interstellar travel seems to us now. The radio had only recently been invented. Powered flight was 20 years old. The expansion of the universe was not yet established. The structure of the atom was still being worked out. From the vantage of 1925, almost everything we now consider routine in space exploration would have seemed implausibly distant. And yet here we are, with 2 spacecraft already in interstellar space, with a fleet of rovers and orbiters scattered across the inner solar system, with telescopes detecting the atmospheres of planets around other stars. Not because the laws of physics changed, but because we slowly accumulated the engineering, the institutions, the funding, and the patience to extract the maximum possible reach from those laws. This is worth remembering when we contemplate the wall between us and Proxima Centauri. The wall is real, it does not move. But our position relative to the wall does move, slowly, generation by generation, as we develop better tools and deeper understanding. Whether we will ever cross the wall in any form recognizable as human travel, I do not know. Whether we will eventually push ourselves close enough to the wall to send instruments across it, even if we cannot follow them, seems plausible on long enough timescales. The interstellar probe currently being designed by NASA may launch within decades and reach distances no spacecraft has yet achieved. Successor missions, building on what that probe learns, may push farther still. Across centuries of patient development, with no single breakthrough, but with the steady accumulation of capability that civilizations are sometimes capable of, our reach may extend further than we can presently imagine, even if it never extends to where our science fiction has placed us. Or it may not. The constraints I have described tonight are severe enough that they may simply close off entire categories of future achievement. We may be living in the species that learns, with finality, that the stars are not for us. That recognition, if it comes, will not be a failure. It will be a maturation. It will be the moment our civilization stops pretending the cosmos owes us anything and starts asking, instead, what we can do well within the home we have actually been given. That is a healthier relationship with reality than the dream of cosmic conquest. It is a relationship built on what is, rather than what we wish were so. And relationships built on accurate perception tend to last longer than relationships built on illusion. Whatever the outcome, the work continues. Tomorrow morning, somewhere on Earth, scientists will be analyzing data from telescopes pointed at the Alpha Centauri system. Engineers will be drawing up plans for the next generation of probes. Theorists will be working through the mathematics of propulsion concepts that may or may not ever leave the page. School children will be learning the names of planets they will never see. Astronomers will be discovering new exoplanets, refining the catalog of worlds that exist beyond our solar system. None of this work depends on whether we ever physically travel between stars. All of it expands our presence in the cosmos in the only way the cosmos seems to permit. And on the largest scales, on the scales that matter to a species rather than to an individual, the question of whether any one of us walks on a planet around another sun is less important than whether our descendants continue the project of understanding the universe at all. A civilization that maintains its scientific tradition for 10,000 years, even confined to a single solar system, will know things about the cosmos that we cannot currently imagine. A civilization that maintains it for 100,000 years will have refined its instruments, its theories, and its observations to a degree that may make our current understanding look as primitive as cave painting. A civilization that lasts 1,000,000 years, even without leaving its home star, will have become something we can barely conceive of, simply through the accumulation of knowledge over time. The interstellar trip is not the only measure of cosmic achievement. The slow, patient growth of understanding may be a deeper one. This is the gift hidden inside the wall I have spent these hours describing. Confinement to one solar system is not confinement to ignorance. The cosmos remains visible to us in its full vastness, even though most of it is unreachable. The data continues to arrive. The light continues to travel. Every photon that reaches Earth from a distant star is a small message from a place we cannot visit, carrying real information about what is there. Across the centuries, those messages accumulate into an extraordinarily detailed picture of a universe whose inhabitants we cannot meet, but whose structure we can come to know. There is no expiration date on this learning. There is no point at which the cosmos says, "You have learned enough now, no more is permitted." The learning continues for as long as we continue, and the thing being learned is the largest and most ancient thing there is. So when I say that reaching the nearest star may be physically impossible, I am not saying that our cosmic future is foreclosed. I am saying that our cosmic future may take a different shape than the one we have been culturally trained to imagine. It may be a future of deepening understanding rather than expanding territory. It may be a future of stewardship rather than colonization. It may be a future in which we become wiser inhabitants of one solar system rather than restless wanderers across many. Each of those futures has its own dignity. Each of them is worth pursuing. Each of them gives meaning to the conscious presence that has somehow arisen on this small planet around this ordinary star. The night sky over your head, when you eventually look up at it again, will not have changed because of anything you have heard tonight. The stars will be in their places, glowing as they have glowed since long before our species existed. Proxima Centauri will be there, 4¼ light-years distant, sending its faint red light toward us across the dark. The Alpha Centauri pair will be there beside it, brighter, more sun-like, already known to be a binary system whose two suns have been orbiting each other since long before Earth existed. The other stars of our local neighborhood will be scattered across the heavens, each of them a destination we cannot reach, each of them a permanent neighbor whose presence we share without ever meeting. The Milky Way, on a dark enough night, in a dark enough place, will stretch across the sky as a band of distant light, the combined glow of hundreds of billions of stars too far away to resolve individually, but close enough to contribute to the soft cosmic illumination that has pooled overhead since long before any human eye looked up. This is the cosmos we live in. It is mostly unreachable. It is also beautifully, generously, abundantly available to our awareness. We can know it without going to it. We can love it without owning it. We can study it for as long as our species exists and never exhaust its capacity to surprise us. The wall between us and the stars is high. The window through which we can see the stars is wide open. And the slow patient looking that has occupied astronomers for millennia and will continue to occupy them for millennia more, is its own form of cosmic participation. Whether we ever reach the nearest star, whether any human ever stands on a world warmed by another sun, whether our descendants ever take their place in some interstellar community of minds, I cannot tell you. I can tell you that we are here now, that we are aware, that we have built instruments capable of detecting the faintest signals from across cosmic distances, that we are continuing the work of comprehending a universe that is in almost every respect larger and stranger than anything our predecessors imagined. That is enough for tonight. That is enough for any night. The work continues, and the cosmos continues. And you, and I, and all of us continue, here, in our small, warm pocket of the universe, looking outward at the dark that surrounds us and finding it, on close inspection, full of light. Thank you, as always, for spending this time with me. Deep Space Signals exists because of viewers like you who choose, again and again, to face the cosmos as it actually is. If you found something in this exploration that stayed with you, a like or a subscription helps more than you know. And the next time you find yourself outside on a clear night, take a moment to look up at the sky and locate any star you can, any one at all. That star is unreachable. That star is also yours, in the only sense that the universe allows. It is shining for you, across distances no human will ever cross, sending you a message that began long before you were born and will continue long after you are gone. Receive the message. Be at peace with the limits. Be grateful for the looking. Sleep well beneath the unreachable stars. They have always been there, and they will always be there, and your awareness of them is the closest thing to interstellar travel that the universe seems willing to grant. It is, I have come to believe, more than enough.